Today we are talking about section 8.1. So we're finding angle measures in polygons, not just triangles. What we're used to is dealing with the fact that in a triangle, all of the interior angle measures, when you add them together, they equal 180 degrees. However, that's not the case in other shapes, like quadrilaterals and pentagons and things like that. So today we're going to see how we can find the angle, the sum of the interior angles in other shapes, not just triangles. So to do that in class, we already started an activity. We drew out a pentagon, a hexagon, and an octagon. And we divided each shape into several triangles. So the pentagon with 5 sides, we formed 3 triangles. In a hexagon with 6 sides, we formed 4 triangles. And with an octagon with 8 sides, we formed 6 triangles. So 1, 2, 3, 4, 5, 6. Now, we know that each triangle has a measure of 180 degrees. So in a pentagon, we have 3 triangles, 180 degrees each, for a total of 540 degrees. In a hexagon, we had 4 triangles with 180 degrees in each of them, for a total of 720. And with an octagon, we had 6 triangles for a total of 1080 or 1080 degrees. And we noticed a sort of pattern. In order to find the angle sum in any shape, when we broke it up into triangles, we took the number of sides and subtracted 2. So 5 minus 2 gave us 3, this gave us 4, this gave us 6. So we took the number of sides and took away 2. Then, whatever that number was, we multiplied it times 180, and that gave us all the angle measures, the total, inside of that shape. So with an octagon, we got 1080, 720, 540, etc. So that leads us to this theorem that has been proven before. That Theorem 8.1, the polygon interior angles theorem, the sum of the measures of the interior angles of any convex n-gon or polygon is the number of sides minus 2 times 180 degrees. Now, as a review, convex means everything is pointing out. All these vertices are pointing out. Nothing is hating in anywhere, like a concave polygon. So, in this case, since we have 6 sides, and this is a hexagon, to find the sum of the interior angles, we would take our formula, n minus 2 times 180, and plug in the number of sides. So 6 minus 2 times 180. 6 minus 2 is 4. So 4 times 180. And that means our result is 720 degrees. Excuse me. It's a very basic principle. We'll go through several different types of examples that involve it, but it's pretty straightforward. So triangles have a sum of 180 degrees for the interior measures. For everything else, we use this specific formula. Let's do another one. Find the sum of the measures of the interior angles of a convex octagon. So we'll start with our formula to find the interior angle measures of a polygon. And since this is an octagon, we have 8 sides. So this is 8 minus 2 times 180. And to use our order of operations, we simplify what's in parentheses first. So 6 times 180. And that ends up giving us a result of 1,080 degrees, or 1080. And usually I say 1080 because back when I was a younger person, I used to do a lot of rollerblading and doing tricks off of ramps and things, and usually that's called the 1080 when you do several complete turns. When you do a 1080, I want to say it's 3 spins, 3 complete spins. And it was called a 1080 trick instead of a 1080. Anyway, but to get back on topic, that's one type of example. Another type is, let's say that we're given the total of the angle measures. And we need to find the number of sides. How could we do that? Well, I'll show you the long way and then the short way. Let's do number 9. So let's say I know I have a polygon, and all the angles on the inside add up to 900 degrees. I want to find the number of sides. Well, I know the formula says that n minus 2 times 180 will equal the angle measure on the inside. So n minus 2 times 180 for this one, for number 9, is 900. And from here, I can solve the equation for n, the number of sides. I can divide both sides by 180. So these cancel, and I have n minus 2 equals, let me double check that, 900 divided by 180 is 5. And then add 2 to both sides, n is 7. So that's a heptagon. If you are a person that likes to think quickly instead of having to do something like an equation like this, what we did was that we divided by 180 and then added 2. So you can always write this. So for example, if I were going to do number 11, I could say n minus 2 times 180 equals 2,520. And then solve my equation for n and end up with 16. Or if you'd like to just do a shortcut, you could do 2,520, divide that by 180, and end up with 14, and then take 14 plus 2 and get 16. So you can set up an equation and solve it, or just divide by 180 and add 2. Let's try something else. Not this one, this one. I'm going to modify a question because you all did a great job in class with this one. Okay, so the question says, what is the measure of each interior angle of a regular nonagon? Well, regular means all the angles are equal, and nonagon means 9 sides. So I'm going to try drawing this out as best as I can for a nonagon. Something like that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 congruent angles because this is regular. So what's the measure of each one? Well, I know together I can do 9 minus 2 times 180, and that will give me the total angle measure of all of those put together. So if I take 9 minus 2, which is 7, and multiply that times 180 degrees, this ends up being 1,260. That is the sum of all of these angles together. But these are all equal. So I can take 1,260 and divide that into 9 equal parts. And if I do that, each angle ends up being 140 degrees. And that's my result. So again, I know that since I have a nonagon, all of those angles together is 1,260. Since it's regular, I know every angle is the same. So I can just divide 1,290 into 9 equal parts, and each of those parts is 140 degrees. So that's kind of a brief few examples dealing with this idea. There is one other main idea we need to look at, and that is talking about exterior angles. So the sum of the measure of the interior angles was that formula we just looked at. The exterior angles remains consistent no matter if it's a pentagon or a triangle or a hexagon or whatever type of shape it may be. All the exterior angles always add to 360 degrees, no matter what shape it is, as long as it's a convex polygon. So here, with this pentagon, these 5 exterior angles will add to 360. If I had a hexagon, and I made some exterior angles here, I'll have 6 of them. And all 6 of these will add to 360 degrees. So you might be asking yourself, well, there's more angles. Why do they still add to 360? Because the more exterior angles you have, the smaller they end up being. So these angles end up being smaller than these angles. So there's more of them, but since they're smaller, they'll still add to 360, no matter what. So let's look at an example of that. We're going to find the value of x. Well, here, I don't have to count the number of sides because it doesn't matter. these exterior angles always add to 360, no matter how many sides the shape has. So I can add all of my angles here, and when I add them all together, it should equal 360 degrees. I can combine like terms, and I have 3x plus 156 equals 360. And if I end up solving for x, x will be 68 degrees. So that's just a brief overview of the main topics from this section. If you need any help, feel free to send me an email or come in before school at 7:30, or you can come in after school if it's a Monday or a Wednesday from 5 to 5:30.